Okay, welcome back, everybody. Okay, well, I don't know. I don't have any administrative things that have come up during the break, but I did have another look at this blog post that I've linked. I think it's a reasonably, nicely honest description of this question. Like, you don't have to use an object relational mapper to make a thing work. You can just do database queries. Interestingly, this is a Go, like in the Go programming language example, which is a funny one because Go is not like object relational mappers are kind of inherently about objects. Go doesn't have classes and objects the same way. So it's going to be inherently a funny fit just because of the programming language, but that's another course. I think there is this okay, well, we could, accept some help from this object relational mapper, which is probably what's happening here. This is a composition sort of almost superclass thing in Go that I'm going to use the gorm.model, not quite superclass, and then put these things in my structure, which are going to map onto a database table. Or I could write some SQL queries, right? And say, well, give me all of these things where something, and then I will iterate through them and build the appropriate objects as we go. Sure, could do. And yeah, in general, an object relational mapper, it's another thing to learn. You know SQL, you don't know ORMX. Less people are using it. I understand I understand why this point is here. It can be hard to debug. Like, why is my ORM producing this stupid query? Okay, you have this layer of abstraction to unroll before you get down to, oh, this is the query it's producing. Did I do something bad, or is my ORM bad? I have to sort of compensate. I think it's a reasonable point, but I will leave you with that. The thing that I see developers doing incorrectly the most often by far with an ORM is this n+1 queries problem. The same thing that was back here a few slides, this. So when I said this, just as oh, don't do this, do this instead, join and make one query where, as opposed to making n+1 queries, that's obvious. I think when I say it that way and I just say, oh yeah, here's some code, don't do this, but that's not the way the code is going to look. The code is going to look like this. So I'm imagining, I guess, a Ruby on Rails example here. This is whatever ERB stands for, an ERB template. That is what Ruby on Rails uses. So this is, I have a collection of people, which again are presumably coming from some ORM, like this, right? So I have a table, I have an ORM, and I say, give me all of the people that have some property. And then I go to my HTML template and I pass that collection over and I say, okay, well, render it as HTML. That's the story being told here. So for all the people, create a list item, first name, and then what department they're in. This seems totally reasonable. And because of this foreign key here, you're probably writing this code. You're going to create the collection of all of the people, but then you get to this moment and the ORM realizes oh, you want that for you. You told me I have to follow that foreign key now. I have to find the person's department. So now I have to go and do a little subquery of well, what department goes with that person's foreign key? You can overcome that. And again, I think people either don't notice at all, or they think, wow, this ORM is really slow. When I had 5 people in my database, it was fine. When I had 100 people in my database, it was noticeably slow. And when I had 500 people in my database, users were complaining because pages are timing out. All you have to do is sort of not lazy load that department, right? So in the Ruby on Rails ORM, that's this, give me the people and like prefetch all of the departments that go with them. It's the equivalent of this, like join while you're doing it, and join in the obvious way. It's a one word change almost, but it's the difference between, again, pages timing out because something isn't allowed to take more than 30 seconds and as fast as you can deliver the bytes to the user. If you're in, let's see if I can write the same code in Django, it would be people equals person objects. Okay, so this is the n+1 queries version where none of the related objects are preloaded. And if I go to my template and I look at it, or I have some loop over this collection, I look at the departments, I have to make a new query for each one. And that's all. That's the only difference, but you have to remember to do it. The problem is it works either way. And I have found myself, honestly, more and more sort of overcoming this abstraction by not testing with 3 records. Like having some code that generates 100 records, it randomly generated data or whatever it is, but I want 100 records in the table I'm testing with, or 200, not 3. Because again, if I have a couple hundred records in my test database, I'm going to notice if I get this wrong, because I'm going to be clicking around and testing my page and it's going to go, and the page is going to load. I'll notice. Maybe this is the wrong abstraction. I don't want to test with unrealistic amounts of data. Anyway. I've been talking about all this stuff, and again, like, they're all interdependent. It's very hard to choose an order, but I've gone with this one. MVC is, in some ways, what I'm doing here is like leading into the technology evaluation that we're going to start in a few weeks with the presentations, because a lot of you are going to be choosing ModelViewController kind of technologies. What I was just talking about was really the model part. And I kind of have been implying these things or referring to them without defining, but let's talk about them now. So, and again, you might have seen ModelViewController in some other course. If so, fine. You'll be bored for the next couple of minutes. But in a ModelViewController architecture, and you'll see various like different interpretations of the term or slightly different acronyms, but the same fundamental ideas are hanging around, which is I have some data, and maybe my data is being managed by an ORM, right? So maybe I have too many. It's hard to stay at 2 spots and slide. So maybe my model is going to look like this. I have an object-oriented kind of programming language. I have a database. Those both seem very likely. Well, an ORM is then a very reasonable way to put those 2 things together. The ORM sort of becomes my model layer. And for this, we go back to 225 or 354, or if you've transferred data structures and algorithms and databases, and we design the class, we design the table or the relational database. I imagine if you do those things right, they're going to look about the same, and the ORM is going to connect them to each other for free. That's great. One thing I will point out, like, there's nothing here, there's nothing in the model layer about web pages, right? There's nothing on this slide that says we're making web pages. We just have data, and we could send them to web pages. We could make a phone app or whatever. The view layer is about presenting information to the user. So again, in general, this could be like a desktop app and you like pop up a window or, whatever, or a command line thing. But for us, it probably means web pages. And I guess I mean, well, maybe I'm being a little too specific on the slide here. Generating HTML somehow, maybe it will be generated on the server, maybe it will be generated by some JavaScript code in the client, but one way or another, I need to present data to the user. The presentation, or the way we're going to represent the information, is HTML. It's going to get styled with CSS, like all that stuff we talked about earlier in the course. In order to display it to the user, we need some concept like I had back here a few slides, which is, okay, well, for each thing in the collection, generate this HTML, an HTML template. So I guess I had that ERB example back there a few slides. This is a handlebars template. So it's often something like this. And again, I guess I don't really care if this is happening server side or client side. I always imagine it happening server side so that on in my Ruby on Rails code or my Django or CakePHP or like whatever server side framework, I have this template and I have a data structure or a collection of data structures, like, you know, collection of directions in an array or list or whatever, and I have a title. I'm going to take out those pieces of data in my programming language and somehow sort of send them into this template. Somebody is going to turn this template into actual, you know, a string, right? A collection of HTML that we can send to the user, send to the web browser, and display. I think this is reasonably obvious what's going on here. And I guess the story is the same whether I do this on the server or the client. If I'm doing it on the server, I'm sending this string over the network. If I'm doing it on the client, I'm sending the data over the network in some like machine readable way so that on the JavaScript side of things, I have these values, these data structures, lists, arrays, whatever they are. And then in the web browser, I turn that data into markup. I don't really care. Like the same idea. It's still, in my mind, it's still a view. It's still a template, no matter where you render it. Concept is the same. The controller is the thing that's in charge of sort of dealing with the user's actions. Again, if you're writing a GUI app, it might be clicking a button or dragging or something. If we're imagining things happening mostly on the server side, the user action is an HTTP request comes in. So the user comes along, they make a GET request for this URL with these headers like we saw a couple of weeks ago. And then on your side, like in your code that's running on the server, something is in charge of saying, okay, well, when URLs like this come in, I'm going to call this function. So if this URL gets requested, something maps this string onto this function call. You know, it's like I have schools / string that represents a record in my database / this, and I'm going to map that over to this function with some kind of routing, dispatching thing that's probably, again, part of my MVC framework. If I'm imagining this happening on the client side, user action is more likely a click or a drag or a whatever, like actually the thing that maybe I think more of as a user action. And then I have some kind of like, okay, when the user does this, I want to update the page this way. This template, again, on the client side is going to turn into HTML, or we're going to get some data from the server and then put it into this template. It's similar. It's going to be like some kind of request from the user, maybe not an HTTP request in a URL, but some kind of request from the user maps onto this logic or this content or this display. So the controller. On like one way or another, we need data. So I guess when I said that, I was imagining a GET request and a view, like just a display the data kind of operation. It could be a post request or a request to modify the data, an update, whatever it is. This is now, I guess, your responsibility as a programmer to deal with appropriately. Again, if it's happening server side, it's going to be probably find all the relevant stuff in the database, take the HTML template and send HTML back to the user. If it's happening client side, it's going to be make a request to the server for the data one way or another. So go to the server and say, I want this data, get it back as a JSON object or whatever, turn it into JavaScript variables or JavaScript data structures, and then do this on the client side and just show it to the user in whatever way your client side framework does. But again, either way, it's the controller doing its thing. It's this action the user took turns into this thing, and we'll show them the result. Again, as we sort of transition 2 weeks from now into the presentations for the technology evaluation, we're going to get these different terms for, honestly, in my mind, the very similar things. ModelViewController, Django uses ModelViewTemplate, although Django uses view to mean what I would call controller and template to mean what I would call view, I guess. MVP is ModelViewPresenter, which I want to say is somewhere in the Java world. I don't remember where. ModelViewViewModel, which is three words, even though it's 4 letters. Angular maybe is ModelViewViewModel. Things get a little more complex when you're on the client side because you're getting data from the server and you have data on the client and they have to get linked together somehow. Or you have to link them together manually one way or the other. But again, I'm going to assert that these concepts, model, view, and controller, there we go. I'm sorry. The concepts are the same. Maybe there's another layer of complexity on there or something, but different people call them what they want because they want to emphasize different things, or they want to emphasize that their workflow is this way because that makes sense for their way of abstracting the universe or whatever it is. But I'm going to say those same concepts are buried one way or the other. Okay. We have relational databases, right? And I've told this whole story as if we have relational databases. And these are the kind of things we need, I guess, as we scale, right? So that whole story I told is perfectly reasonable. Frankly, if you're not a bad developer, like if you just do things reasonably, you use your database well, you're not dumb about it, you don't abuse your object relational mapper, all of these things are tens and hundreds of thousands, maybe millions of users kind of scalable. Like database servers are really good at what they do. But what if we have more? What if we do sort of grow beyond that limit? Well, we have maybe lots of reads and writes, hundreds, thousands per second. Maybe the amount of data is not megabytes or gigabytes, it starts to be terabytes. It's very hard to have one database server that's capable of handling either one of those two things at some scale. The other thing that is difficult at some scale is if I have one database server, it has to be somewhere, right? It is somewhere on the planet. I guess in my story here, it's in Vancouver, or I guess I don't know how precise my errors are. But let's say it's in Vancouver. If I have a user in what's like the farthest thing away, like India, Sri Lanka, Madagascar, something like that. Here's the problem. If I want to go, like the user makes a request to me, and then I send a response back, the worst case scenario is like that's one full like circumference of the Earth. The fastest I can possibly send that data is the speed of light, and I'm at 134 milliseconds. That's a noticeable amount of time. Like the speed of light is actually on that scale surprisingly slow. And I guess, like, honestly, one of the problems here is that too many developers live kind of over here and forget that they have users over here. I think, if there were more server farms in Sri Lanka, we might in Vancouver have a better idea of like, wow, making a request to a faraway server actually takes a noticeable amount of time. Or if we were in Australia or something, maybe we would remember that a little more. And that this is going to be true of like web servers, but at the moment I'm talking about database servers because in the story I've told so far, I have one database server. So I kind of have one point on the globe where my data lives. And of course I have all of these other things happening. But if I just want to make a request to my database, and whether it's HTTP is the thing flying around the world, or if like I have a web server over here and it has to request to the database over there, I'm going to have this kind of time scale plus a little more. So if I have one database server in one spot and I'm trying to do all of these things, I kind of have to have one database server in one spot, don't I? Right? Because I have to lock. If I'm going to do global consistency perfectly, like one way or another, I think I have to have a lock. Citation needed, but feels true, doesn't it? And what if I have a failure, right? So what if in my picture of the globe here, wherever I have my database server over here, somebody outside with a backhoe digs up the fiber optic cable? Am I out? What do I do? So that is going to be hard. And I guess the other thing that I'm going to assume about relational databases is I'm going to have relations. If I'm going to have relations, I'm going to join tables because I want to follow those relations and put them together. That's the whole point of having a relational database. I want to do joins. At some scale, joining becomes hard. And if I do want more than one database server, which again, maybe I want because of volume or velocity, maybe I'm going to have to partition things somehow. I'm going to keep, I have 10 database servers and I'm going to kind of keep 1/10 of my data on each one or something. How do I join that together? Even if, again, I get away from a single server, how do I join across multiple servers? So, okay, again, at some scale, we're going to have this problem. And I'm going to tell two stories here. One that leads to non-relational NoSQL databases, and another one. So maybe the problem is this just doesn't work at some, again, if I have thousands of users, it's not going to be a problem, frankly. Millions of users, tens of millions, hundreds of millions of users, boy, maybe I just can't realistically ask for those things out of my database. I have to give it up, or at least some of it up. So you go through those thoughts in like 2005 or whatever, and you say, well, I'm going to give up some relational stuff because it's just not working for this use case, and this is NoSQL. And again, I don't know if NoSQL is a term that comes up in the database course, probably not universally. Basically, NoSQL means non-relational databases that are 15 years old or less. Like the non-relational databases of the 70s that were in some chapter at the back of your databases textbook. That's not what we're talking about here. These are the non-relational databases of this problem of we've got a whole world and we've got terabytes of data and thousands of requests per second or thousands of queries per second to deal with. So for just engineering reasons almost, we're going to relax some of the things we expect from relational databases in the name of performance. So NoSQL describes this huge variety of things that are not in any way uniform, but usually we're going to simplify things. Again, usually. Most NoSQL databases don't have foreign keys. They're non-relational databases. So we don't have foreign keys. We're probably not going to join. That's what foreign keys are sort of there for. So we simplify. We have tables, but we don't have relations. But if we can't join data, you end up saying, well, but I want, like the thing you would have done with a join, which is say, well, I want this data and this data together when I query. Well, maybe now I have to put it together. I have to store it together. And then I have denormalized data. I have a copy of that fact here and I have a copy of that fact there. That's not awesome. It's hard to maintain and hard to update, but maybe you have to. Maybe you have no other choice. Maybe I can't have all the ACID guarantees. Maybe I just can't have completely consistent queries. Because again, if I want to be consistent, and this is if I at the same nanosecond in time make a query in Vancouver and I make a query in Australia and I make a query in Germany, I have to have exactly the same results. Well, I have to communicate between those places somehow to make sure we're all being consistent. Maybe I can't do that. Right? I have to give up consistency, or at least weaken what I think of as consistency. And the goal here, and the thing that I hope to get in return, is I can have, what was my example again? I can have database servers in Vancouver and Germany and Australia, and a user can be sort of sent for their data to whichever one is closest. So I have maybe some distributed data. Again, I give up consistency, but I get to sort of not have that speed of light between my farthest away user and my one database server. I have many database servers that somehow are consistent enough. And for durability, I guess maybe I need some redundancy, right? I can't store one fact in one spot because it has to be kind of close to different users, but I get redundancy out of the deal. Again, if I have 10 database servers, well, I have 10 times the chance of failure tomorrow. Something's going to fail. Some redundancy would help that. And well, my query language that's built around relational databases maybe has to, I've got to give it up or modify it or something. So like I said, there's this huge variety of non-relational databases that get put in the NoSQL category. Even things like graph databases, things like caching layers like memcached, which are probably not what I'm talking about here. I'm thinking about things that are a little more durable than in-memory cache. But if having no other information, if I was choosing one, it would be Cassandra. Cassandra is, it's an Apache project. It seems to be well engineered. It's open source. It's distributed. It's scalable. It does the things I want from a data store, but not SQL, not relations. But you do get the Cassandra query language, which, boy, that looks a lot like SQL, doesn't it? Like these are valid CQL queries for a Cassandra database. And they are also valid SQL queries, but there's no join keyword. Right, there's no join, that's true. There's a group by, but group by is very, very limited. It's not the group by that you know from the database course, and there's no transactions. So I can't sort of do two insert operations atomically. I can do one insert operation and then another one. You can even do something called a batch that is many inserts put together, but they're not atomic. There's no concept of a transaction. Okay, I don't want to give those up, but maybe I have to. What I get out of the deal is something like replication. So I get to say like each individual row should be stored in 3 places on 3 separate servers. So again, one server's power supply fails, I'm still good. I still have all my data there. And you can also say things like every record has to be stored in 2 servers in Vancouver and 2 servers in Germany and 3 servers in Australia. Like that's something that can be expressed in this ellipsis that I haven't said here. So you have all that. And again, if you need to read or write, you have this choice of, then you can do it from the closest server or whatever. And the other thing that I sort of said we were going to give up here is, again, some of the ACID guarantees. So we've already given up atomicity. Atomicness, however you pronounce it. So we have a consistency question, isolated, durable. Oh wow, that's how long have I been teaching this course? I think that's the first time I've ever remembered what all 4 ACID things stood for while giving a lecture. Somebody note the date. Anyway, so we're gonna play with our concept of consistency a little bit here. And what we're gonna do is choose. So I can say for every query, either a read or write query. So this is, I'm about to insert something into the users table. A new user has registered for my system or whatever. And what I'm going to choose here is at least half of the servers have to receive that row. So if I'm going to store, the row in 3 places, like two of them have to receive it and say, okay, I've got it written to disk before this query is allowed to sort of complete, before I can fire another query and it returns a success. Or I can say any one server. So if I'm going to store it in 3 places, one server has to receive that before this query can claim to be successful. And I have a bunch of choices. I can say everybody that is, again, everyone who is supposed to write that row has to receive it, or any two, or any 3, or if I'm reading, I have the same thing. Like if I'm going to do a select operation here on my users table, I have to check, like if 10 servers have this record, I'm going to check all 10 servers and make sure everybody agrees. Then I'm going to finish my select query. Or I'm going to check with half, or I'm going to check with 1. And I have that choice per query, which is really cool. Because I can say, like, okay, if a new user is going to register, that's important. I'm going to go n-1. But if I'm going to read how many upvotes are there on this post, well, who cares? Like if I'm wrong or I'm out of date by a little bit or whatever, I can have this partial or like kind of a weaker idea of consistency, which is I'm willing to be kind of a little bit out of date on this query, consistency any, and then select how many upvotes are there on this post. And I can choose. I never had that choice before. Now with Cassandra, I do. I have this whole different engineering choice now. I can choose a database that has these distributed servers. I can scale. I can have terabytes of data. I can have thousands of requests per second. Great, no problem. But I had to give up a lot to get there. And maybe I now have this problem of I need more than one database for my system. I have some data in a relational database. I have some data in Cassandra. I have some sort of in memory as a cache or whatever. That sounds like a lot of work. It sounds like a lot of programming and a lot of just engineering to do to get all of these things working and working together and deployed and reliable and whatever else. It's going to depend on the situation, right? So if you're Facebook Messenger, I mean, you're not Facebook Messenger. There's no scenario in which MySQL is going to handle everything that is going through Facebook Messenger. Or like you can pay Larry Ellison all the money you want. Oracle is not going to handle all the data going through Facebook Messenger. It has to be distributed just because of the size of it. And they've been using, so HBase is also excellent non-relational database, very cool, very reliable, very scalable, very unpleasant to work with as a developer. But hey, Facebook's got the money to pay those developers to do unpleasant things and work with HBase. Or Reddit apparently uses Cassandra or used Cassandra. I never know how up to date these things are. These companies don't always tend to announce it when they change underlying backend tech. But now, yeah, consistency. I really liked consistency. That was like atomic transactions and consistency. I like those. Those are great. And now I guess the choice is how important is my data, right? So if it's a bank, right? So I would really hope that my bank uses a proper relational database, right? When I do a Visa transaction or whatever, I don't want any consistency questions there. I want to know that like we all agree that I got my paycheck or whatever. But again, for something like Reddit, if I'm on Reddit and I click the up arrow, okay, if I click that up arrow and they're using Cassandra, and the up arrow, the fact that I upvoted that thing is written with consistency level any. One of the Cassandra servers in their cluster has to receive that data, and then my little up arrow turns orange, whatever it turns. Okay, maybe the power supply or the disk or whatever on that Cassandra node fails 1 millisecond after I press the up arrow and it gets lost. I am totally willing, and especially if, as Reddit, totally willing. I don't care. Like if, again, some tiny, tiny fraction of upvotes get lost when lightning strikes or there's a power failure or whatever, cool. That's great because it's the only way to scale. I'm not willing to lose some tiny fraction of bank transactions because something went wrong. Again, there's this now extra axis where we have to make choices about how our data is stored and managed. By the way, when I say HBase is annoying to work with as a developer, HBase has one data type. There's exactly one type of data that you can write into an HBase table. It's bytes. You can store whatever collection of bytes that you want. And if you think those bytes represent a UTF-8 encoded string or a double precision floating point, fine. HBase will give you back the bytes. You can do whatever you want with them. And that's really annoying to have to, every time you query a database, manually in the programming language convert all the bytes back into data. But hey, it's scalable because you can do that on 1,000 different servers, and the database doesn't have to scale to do that operation database side. Anyway, so I think it's going to depend on your data. And like I said, there are things like, where'd that link go? Yeah, things like Amazon DynamoDB or Neptune. Wow, it's a very Amazon heavy collection of things here. Or like Elasticsearch, which they've renamed to whatever since this thing was posted. Yeah, actually. So in Relational Database, key value stores are things like Amazon Dynamo that are just, all you can do is look up by key, like a dictionary or a hash table or something. Document databases where what you store is much more like a JSON object than what I would call a document. A graph database where just something like find the shortest path is a first-class operation that you can do. For some data, that's going to be awesome. Or I need full text search. I need to be able to say, well, what are all of the things where this word has been used? And I want that to be really fast. So that's like Elasticsearch or Solr are good at those things. It might depend what you're doing with your data. And you might end up with more than one of them. You might end up denormalizing your data to get there. My one caution here is don't use Mongo. Like every story I've heard, and like I can't fit enough links on this slide, frankly, to properly convey like I've never heard of a developer who chose to use Mongo and then actually had to scale it up like Mongo promises to scale and been happy. If you choose Mongo for your project, you've made a bad choice, and making bad technology choices is something that I think is mark related on the project. There's so many horror stories. Don't choose other relational databases. Okay. On the other hand, you're not Google, you're not Facebook. The number of customers that you have right now is 0, and the number of users you have, on your, your course project or the thing that you're making on the side or whatever it is, single digits or whatever. The reason that something like a non-relational database is hard is that denormalization thing. So you have to choose sort of at the data, like choosing your fundamental architecture for your data. What tables are you going to have? What columns are you going to have? You have to know how you're going to look things up. You have to know that, okay, I'm going to look up by this. So that has to be the partition key in my Cassandra table. I'm going to have to find data by this. So I have to keep a manually generated secondary index in HBase so I can find all the records with that thing and then go to the table by primary key and get them. You don't know that now. Here's the example I like for this one, Twitter. Okay, Twitter has to be able to look up tweets by hashtag, right? We all know, like, we want to be able to go to Twitter and say, what are all the hashtag whatever news stories happening right now, the hashtag Trump or, whatever. I want to find all the tweets with that in them. So we have to index by hashtag. The problem is that was not part of Twitter's design. Twitter, like hashtags on Twitter were completely emergent. Users decided that hashtags were a thing, and you can find the story online, like where did the hashtag come from? And it wasn't Twitter. This was just dumped on Twitter as our users are using our system this way now, so we have to be able to look things up that way. It was logically impossible for them to design Twitter with hashtag lookups as part of their data model, because it didn't exist when they designed their data model. they had to sort of retrofit that possibility to look those up quickly after the fact. So on a lot of these non-relational databases, again, you have to design your data for the queries you're going to do in a very deep way. You don't want to do that, and you can't predict it. Relational databases scale perfectly fine, thank you very much. You know, are you going to be bigger than Twitter was in 2012 anytime soon? No. Let's be honest, no, you're not. Amazon Aurora is, for the user, like your code thinks it's connecting to a MySQL database, like it's the same protocol as MySQL. They will scale more than you would think a relational database is going to scale, in both availability and size and queries per second. You're going to pay for it, but hey. And then there's this slightly newer category. I don't know when the term was coined, relatively recently, 2011. But these new SQL databases that are, you know, I think a result of the relational database world looking and saying, oh, wait, did you want that? We can do that. Like the people, you know, the relational database researchers are very good at what they do. You wanted to do that at scale? Yeah, sure, whatever. We'll call it Cockroach. We'll call it Aurora, whatever. It seems like a horrible name for your database, but whatever. It's apparently very well done. But this is SQL, but at scale, and fault tolerant and everything else. Those are really cool. And okay, maybe they're not as scalable as HBase or Cassandra, but again, you're not Google. You don't need data at that scale. Why engineer for it? Why pay the money to engineer for it? This, if nothing else, this is how many stories are in your data center building. Google has 4. Do you have data center buildings? No. Don't pretend you're gonna design at that scale when you have 1 server, 2 servers. I think this is my honest advice for anybody starting a web project, whether it's you as a project in this course, or again, the side hustle or the startup company or whatever. Use Postgres, use MySQL, normalize your data, use joins, use your ORM not stupidly, and get something working, right? So don't put dozens, hundreds of hours of work into having something that will scale for a use case that you don't even know what that use case is yet. Because it's going to change, and nobody who starts a thing ever has it progress and work exactly the way they imagined. Features that you thought were throwaway features are the ones your users are going to love or whatever. Worry about it later. Worry about it when you do have 1 million users, because then frankly, you can probably hire people to re-engineer things for, 1, the actual things you do, the actual uses you have for your data, and then you can pay them to do it, and you can just be rich and live in a yacht or whatever it is rich people do. So yeah, that's my advice. Honestly, just use a damn relational database. They're really, really good at what they do. I think this quote, which actually seems to be a real verifiable quote by Don Knuth, we only get this one. We only get 97%. But I think the rest of it matters too, right? So programmers do use enormous amounts of time worrying about optimizing things that don't need to be optimized, because either it's not code that is critical, it's not code that needs to be fast because it doesn't run very often, and it makes their code worse. It makes it worse to be debugged and maintained. And again, the advice here is like 97% of the time, just write good code, write beautiful code that's easy to understand and easy to get correct. And then for that small fraction of the time, maybe then worry about efficiency. But again, do it after you've profiled and after you know what's going on and what has to be fast. Don't try to guess ahead of time. Okay, so I think that's a good spot to stop. I will talk about security next week. It's kind of a nicely contained 1 week worth of topic, and then you will start saying things. So yeah, get your technology evaluation topics and start thinking about that. That's probably the next thing for you guys to worry about. And I will see you next week.